We present our work on evaluating robustness of visual representations on our novel object assembly task, geometric peg in hole. Our task consists of geometry-informed object assembly, where the dual-arm robot is tasked to assemble the object parts by its grippers. The object parts have distinct geometry that only allows insertion in a specific position and orientation. The view from the L515 camera up top looks like this. Now we move on to the objectives of the project. First, we learn dual-arm manipulation policies with various vision representations from demonstrations in simulation and in the real world. These policies must perform spatio-geometric reasoning by learning geometric correspondences, symmetries, and expected configurations implicitly from demonstrations. These policies must also be robust to grasp variations in translations and rotations. The policy learning framework is as follows. The top-down view, left wrist view, and right wrist view images are taken from the current time step and pre-processed. Then, these three frames are fed into the vision encoder, producing three image embeddings. Finally, the image embeddings concatenated with the proprioceptive input is fed into a multi-layer perceptron to produce the action to perform at this time step. This process is repeated in a closed-loop fashion until the task completes or times out. We train and evaluate policies based on 8 different vision encoders, including from scratch baselines as well as pre-trained weights from CLIP, ImageNet, and R3M. We empirically show that the from-scratch encoders perform best over all setups varying in difficulty, data quantity, and imitation learning method. We show the collected simulation demonstrations. Note that top-down, left wrist, and right wrist views are collected in simulation. These are successful results with the from-scratch model trained on 1,000 demonstrations. Now we move on to the real-world setup. For each episode, objects are picked up with a random grasp variation. Note that the geometric variations of the parts are not visible before the objects are shown to the top-down camera. Scripted expert trajectories are used to perform the assembly and collect demonstrations. Finally, object parts are placed back on the supporting wedges before grasping for the random episode. Here are the collected demonstrations. We collect 10 episodes for each task variation. Here are the sampled results from successful episodes. Here are some common failure modes for the real-world experiments. First, the model mispredicts the z-axis rotation. Second, the model provides an imprecise estimate of the x-axis translation. Third, the model fails to estimate the y-axis rotation. Thank you for watching.